Welcome to the class. Welcome to the class. If you've just joined into this classroom, this is the National Tutoring Campaign, and I hope that everybody is ready and ready to learn. As you guys know, my name is Nonkululeko Madondo. I am your teacher for grade 11 for these tutoring sessions, and I thank you guys so much for joining in. I know last week we started off with our term 3 work, and we started off with our electrostatics, and this week we're moving on to electromagnetism. So thank you guys so much for joining. Just a few rules for this classroom. If you have any questions, you can just send me on the chat box, and please guys, don't keep quiet until the end of the lesson. Whenever I'm explaining and you get stuck somewhere, you are free to ask on the chat box, and let's have an interactive classroom. If I ask questions, please guys, let's talk, let's make it work, let's learn some physical sciences, and let's get those A's for this term. Okay guys, thank you guys so much. So just an overview of what we're going to be doing. Let me just go to let me just go to our first slide. Sorry about that. I'm just trying to, I just hope that I've got everything intact like it's supposed to be. Okay, so today we're doing term 3, we're doing electromagnetism. As I've explained this chart for us, we just have 1 hour to just get everything ready and make sure that you guys get a grasp on everything. So last week we started with the electrostatics. So this week we are here on the second part of term 3 work, which is the electromagnetism. We're going to deal with magnetic field of an electric current, the environment, and overhead cables. But there we're going to be very selective because we're only doing things that's going to count for you in the end of the year exam. And we're also going to do the Faraday's law of induction. Okay, so what is our overview for today? For electromagnetism, the thing that we're going to be learning about today is number 1, magnetic field around a straight current carrying conductor. Number 2, magnetic field around a single loop simple coil. And then we're going to have magnetic field around a solenoid, which is a coil with many turns. And we're going to do electromagnetic induction and electromagnetic induction by electrical methods. And we're going to do a couple of problems as well, just to make sure that you guys at least know how to solve problems that relate to electromagnetism. Okay, so guys, please make sure, I also mentioned to you guys last week that in this classroom, we're going to be working very closely with the Siyavula textbook. You're going to see some of the examples that I'm going to be using as well. They're going to be coming from the Siyavula textbook. So please guys, make sure that if you do not have a Siyavula textbook, you can download it. It's absolutely free. You can just, go on Google and download Siyavula textbook. I chose that specific textbook because it's accessible to everyone. I know different schools use different textbook, but for us, for the tutoring, we can use that one because at the end of the day, they all cover the syllabus that you guys need to know and prepare you guys for the exam and prepare you guys also for matric. Okay. Okay, just trying to go to the next slide. Okay, so for the introduction, I just have a couple of terms that you guys are going to need to understand in order for you to be able to grasp the concepts when it comes to electromagnetism. What is electromagnetism? Electromagnetism is a study of the properties and relationship between electric currents and magnetic field. Okay, so this is a study. There's people that actually go and study this as a full-time thing, and that is how you need to understand this concept, because guys, the theory is very important because these are the type of things that will be asked in your multiple choice, and on your true or false answers, they will be asking you a lot of these terms. So number 2, we've got electric current, which is the rate of flow of charge. And we know the formula is I is equals to Q over 2. And that is our electric current. And then number 3, we've got the charge carries. In metals, it is electrons. In electrolyte, it is negative and positive charges. So those are some of the terms that you're going to see a lot within this chapter. And a current carrying conductor has the magnetic field around it while the current is flowing through the conductor. And this conductor is called the electromagnet. Okay, so that is very important. So let's get to it. So magnetic field around a straight current carrying conductor. What are we talking about? A magnetic field is an area. You remember a magnetic field, you cannot really see it. So for scientific purposes, we always use these lines to illustrate the flow of your magnetic field. So a magnetic field is formed around a conductor when current is flowing through it. Okay. So you're going to have your conductor, and the flow of the conductor is going to be your magnetic field. So a magnetic field is formed around a conductor when current flows through it. So for example, if this is your conductor, this right here in orange, it's a conductor. So it will have current flowing it, and all of this illustrates the magnetic field around it. Okay, so the magnetic field direction is defined as a direction in which a compass's north pole point. Okay, so you always have 2 points in a magnet. You're going to have your north and your south. Okay, so if you check here, this would be your current carrying conductor, and this will be the direction of your magnetic field. Okay, so it will always be around the current carrying conductor. So you see it goes in different ways according to the direction of your current flow, but we're going to talk more about that as we go on in the lesson. So a magnetic field is formed when a current flows through a conductor. The magnetic field properties are as followed. In a plane perpendicular to the current carrying conductor, number 2 is the strongest closest to the conductor. What does that mean? It means that if you have, this is your current carrying conductor and this is your magnetic field, it's going to be the strongest. This first line here, your magnetic field is going to be the strongest here at the beginning. Okay, on closest to the current carrying conductor. Okay, and then the direction of magnetic field is given by the direction in which the compass needle points. Okay, so the direction of the magnetic field is given by the direction, which is in this case, it's going to be this part. Okay, so you see these small arrows, they indicate the direction of the magnetic field, and this arrow on the current carrying conductor indicates the direction of the current. Okay, so this is your current carrying conductor, and then this is the direction of your magnetic field. So if the current in this case, it's our conventional current, it moves from positive to negative, is reversed, then the magnetic field direction will also be reversed. So you see what that means, guys. Let's come back to this one. You see in this case, your current is moving downwards, but look at the direction. It's going the other way around. But check on the second one, the current is moving upwards, and now it's moving in an opposite direction. So that's what they mean there when they say that the properties of a magnetic field, if current is reversed, the magnetic field direction will also be reversed. It is continuous and it's represented by the magnetic field line. Okay, so this is the magnetic field line will always be represented by these lines and these arrows, okay, to show the direction. Okay, so it's an imaginary line. Remember, guys, you cannot see the magnetic field with the naked eye, so we illustrate it using these lines. Okay, so it's three-dimensional. So when a current carrying conductor is bent into a single loop, okay, so maybe you take your current carrying conductor and you bend it into a single loop, the magnetic field around it forms these patterns shown here. Okay, so this is how it's going to be. Remember, it's going to be bent. So this is going to be away from the observer towards the observer. So this is how it's going to be bent, like this. So it's going to have 2 points that we cut cross sectionally. Okay, so this one here illustrates the current carrying conductor away from the observer, and this one towards the observer. Okay, so this will be the direction of the current and the direction of the induced magnetic field. So if it's going to go from here, this is your current carrying conductor going all the way to this side. So this will illustrate your direction of your magnetic field. So these are the black lines, and the direction of the current is this one that is illustrated as your blue line. Okay, don't worry, guys. I know that you're wondering, how do you know which direction the magnetic field is going? Don't worry about that. We're getting to that. For now, we're just showing the basic concepts on what is going to be done when you illustrate this in a diagram. Okay, so the magnetic field around a current carrying conductor, we're moving to that now. So it says the pattern shows that the magnetic field is like that of a flat disc-shaped magnet with N pole on one face and S pole on the other side. So the magnetic field inside the circle is stronger than outside, as it is an interaction of induced magnetic fields of the ends of the conductor going in the same direction. So near the center of the circle, magnetic field will always be stronger, and the field line will be your parallel lines. Okay. Let me just try and move this. Okay. So basically, yeah, you might find that there's going to be a lot of lines because they are much stronger there. Okay. The field is much stronger there. So the direction of the field lines can be determined with the help of a right-hand rule. Okay, because now I'm sure everybody's asking themselves, okay, I see the current carrying conductor, but how do I know where the magnetic field is moving towards? How do I know how to point my arrows of the magnetic field? Guys, this is very important because this is something that can also be asked in your tests, in your exam. The field lines form a closed loop around the conductor and inside the cold direction. So we always illustrate by showing the south and north pole, and this is the opposite to the direction outside the loop. So this is how the right-hand rule looks like. Okay, so this was introduced in order for us to know the direction of the magnetic field. It says the magnetic field that surrounds a straight conductor has a circular pattern. As you guys have seen in all the examples that we've shown, the magnetic field always is indicated by a circular pattern. So according to the right-hand rule, if the straight conductor is held in the right hand with the thumb pointing the conventional current direction, so in this case, according to which direction your current is flowing, that's where you're going to place your thumb. The curled finger will point in the magnetic field direction. So you see how it is here. So this will show the direction of your current flow, and your coiled hands are going to show the direction of the magnetic field. So it doesn't matter which direction the current flow is going. You always just point your thumb on the current flow, and then the rest of your fingers will be the direction of your magnetic field. I don't know, do you guys understand? If you guys still want me to explain it some more, you guys can ask such questions, but I think it makes kind of sense, especially if you see an example like this. Wherever your your thumb points, it points the direction of the current, and your coiled hands will be the direction of your magnetic field. And guys, don't forget, it's a right-hand rule, so this only applies using the right hand. Don't try and use it on your left hand, otherwise everything is going to end up becoming wrong. Okay, so I hope this makes sense to you guys. So yeah, so this is how it is. So now we're going to move to magnetic field around a current carrying solenoid. Okay, guys, I'm encouraging you guys, if you're getting stuck, just let me know and we can go back and see how we work it out. Okay, so a solenoid is a number of insulated turns forming a cylindrical coil. Okay, so that's what's a solenoid. You always need to know what's a solenoid because you use it a lot, and it can also be asked to you in a test. So this right here is an example of a solenoid. So you see, it's got many turns inside, and it's a current carrying conductor. Okay. So the magnetic field pattern around a solenoid is shown below. Okay. So in this case, your current is moving in that way. So you would know that it goes up all the way and comes out on this side. So this is how it works. So if you had to put your right hand to where the current is moving towards, you'd be able to see that it shows that your magnetic field would be going in this direction. Okay, so what is important here is to know which path your current is going into. Okay, it doesn't matter where it goes to, as long as you know the direction of the current, you will know the direction of your magnetic field. So this is the south and this is the north pole. Okay, I hope that makes sense to everyone, and if it doesn't, please be sure to let me know so that I can explain further. So a current carrying solenoid is surrounded by a magnetic field which is similar to the magnetic field around a magnetic bar. Okay, so you know, usually sometimes you're going to show a magnetic bar, which is what is usually used, and your magnetic bar will have your north and your south. Okay, so this one, in this case, we're replacing the magnetic bar with a solenoid. So the magnetic field around a bar magnet. I will be the current direction, and there's also a magnetic field inside the solenoid pointing from south to north. Okay, so the right-hand solenoid rule can be used to determine the polarity of the solenoid. Place your right hand around the solenoid with your thumb outstretched and your curled fingers pointing in the direction of the current. You see, guys, always your thumb always points in the direction of the current. Then your thumb points in the direction of the north pole of the solenoid. Okay, so this is how it would be. You can even imagine it here just by putting the thumb where the current is going in. You'll be able to see that your coiled hands are pointing to the direction of the magnet exactly the way it's stipulated in this diagram. Okay. So now we're going to move on. We're going to move to electromagnetic and magnetic material. So an electromagnet is a conductor which becomes magnetic when there is a current flow through it. Okay, so basically here we are dealing with two theories. We're dealing with the electric part and the magnetic part. So all of these things, they work together to form to induce electricity. Okay, so electromagnet is a conductor which becomes magnet when there is a current flowing through it. That's why it's called an electromagnet. So not all can be magnetized easily, nor do all substances lose their magnetism equally and easily. So what does this mean? It only means that it depends on the type of material that you're using, whether it's a strong magnet or it's a weak magnet. You understand? So that's what it means. So some substances like iron are easily magnetized and demagnetized, and these are referred to as soft magnetic materials because they easily get magnetized. Other substances like steel are more difficult to magnetize but retain the magnetism longer, and these are referred to as hard magnetic material. So for you to remember this, you can just think about the fact that easy come, easy go, okay? So an iron, it's easily magnetized, but it's also easily demagnetized. So this steel, it takes longer, it's very difficult to magnetize, but when it is, they retain the magnetism for a longer time. So that's why it's called a hard magnetic material. Okay. So what does the strength of an electromagnetic magnet depend on? Number one, they depend on the current in the conductor, the number of coils around the core. Okay. So there's on your conductor, remember, according to what kind of a material it is, the current that's in the conductor, that one also determines the strength of your electromagnet and the number of turns around the core. Okay, so just like a solenoid, where we mentioned that these number of turns, they also determine the strength of your electromagnet. So the type of substance used in the core. So that one is also important. You need to make sure that you know these things, because these are questions that can also be asked. The strength of your electromagnet, it depends on the current in the conductor. It depends on the number of turns around the core and the type of substance used in the core. Okay. So guys, don't forget, if you have any questions, let us not leave you behind confused. Just make sure you ask so that you can get all the clarity. Okay. So now we're moving on. It says here, electromagnets come in variety of sizes, shapes, and strength, and some are used in large variety of applications. So some are used in like lifting magnets, electric bells, relays, loudspeakers, telephone receivers, tape and video recorders. So electromagnets are used a lot in all these applications. Okay. So now we're going to move to the electromagnetic induction. What is electromagnetic induction? So now we go back to an old scientist who once discovered, who came with the name Faraday's law. His name is actually Faraday. So it's Faraday's law states that if a magnet is moved relative to the coil, an electric current is induced in the circuit by a process of electromagnetic induction. Okay. In fact, an EMF is reduced, which causes a flow of current in the closed circuit. So that's Faraday's law. It says that if a magnet is moved relative to a coil, an electric current is induced. Okay. So just like we mentioned before, that when you place a current conductor on a magnet, relative to the magnet, an electric current is induced in the circuit by a process called electromagnetic induction. In fact, an EMF is reduced, which causes a flow of current in a closed circuit. So the induced current flows only while the magnetic field moves relative to the solenoid. For example, when there is a change in the magnetic flux linkage on the solenoid, and the direction keeps changing, hence it's called an alternating current. Okay. Are we all still good together? So how do we determine the strength of an induced current increases? How do we determine the way the strength increases of the induced current? Okay. So the strength of the induced current increases when, number one, the speed of movement of magnet relative to the coil increases. So you can increase your magnet, okay, by adding a stronger magnet that has more electric fields. Number two, the magnetic flux linkage is increased. For example, using a stronger magnet, okay? And the number of turns on the solenoid increases, okay? So basically, what they mean here is that because you know we've got also have a magnet in here, if you use a stronger magnet, or you increase the number of coils in there, okay? So those are the three ways in which you can increase the induced current, because at the end of the day, that's what we want to do. We want to induce current so that, for example, your appliance can move and electricity can work, okay? So on Faraday's law, an equation was derived. It says the magnetic flux is given as follows. Okay, magnetic flux is equals to the magnetic field times the area. Okay, so this is an equation that you're also going to be work with, and you'll see we'll do a lot when you do the problem of magnetic flux. So any change in magnetic flux induces an EMF. Okay, so an EMF is induced when magnetic flux changes, and this process is defined as electromagnetic induction. So any change in magnetic flux induces an EMF, and that is known as electromagnetic induction. So Faraday's law of electromagnetic induction states that induced EMF, which is showed by this sign, is directly proportional to the change in flux, and inversely proportional to the change in time. Okay, so there has to be a change in flux. Hence, this is the change there is placed on the equation, because there has to be a change in flux for the EMF to be induced. You can't just have a constant flux. If it's a constant flux, then it's no longer electromagnetic induction. Electromagnetic induction is when a change in magnetic flux induces an EMF. So if a coil has n number of turns, for example, n number of turns in this case will be these number of turns. You see here, there's many turns. That is the number of turns they are talking about. The magnetic flux is directly proportional. So the equation of the EMF induced is stated as followed. Okay. So this is going to be your induced EMF is equals to number of turns times. Okay. So if you know this equation, you can know how to explain the Faraday's law of electromagnetic induction. So make sure, even if you forget it, guys, at the back, you check on your formula sheet and you see the sign, you'll be able to define what is the electromagnetic induction. So let's move now to next one. So we've got two. We've got the Faraday's law, and then we've got the LENZ'S law. The direction of induced current, the LENZ'S law, it states that the direction of the induced current is such that the magnetic field established, the magnetic field is established tends to oppose the cause of the direction. Okay, the direction of the induced current is such that the magnetic field it established tends to oppose the cause of the induction. So if a N pole approaches the coil, like we see here, we've got our N pole, it's approaching the coil. A N pole is induced in the coil in order to oppose the approaching magnet. Okay. So, and using the right-hand rule, solenoid rule, the direction of the current can be determined. Okay. So using your right-hand rule, you can be able to determine the current. Because if you check here, do you see just by looking at this picture here, you see here, you can point, you can put the tip of your right-hand thumb here and coil it. You'll be able to see that the magnetic field is going on this direction. Okay. And if you turn it down, you'll be able to see using your right-hand rule which direction your magnetic field will be going into. Okay. And then now we move to some of the induction, electromagnetic induction by electrical methods. You know, there's always different methods that are used, but this one more specifically, at least it's still within your syllabus, is something that you need to know also for your exam, is that when current is available, for example, DC from a battery or AC, a changing current can be used to provide a changing magnetic field, which is necessary for inducing another current in a second conductor. Okay, so you can put two conductors, and by electromagnetic induction, a changing current can be used to provide a changing magnetic field, which is necessary for inducing your second conductor. Okay, so that is electromagnetic induction. So the phenomenon that occurs when an EMF and therefore a current is induced in a coil by means of the changing magnetic field caused by current changes in a neighboring coil is called a mutual induction. Okay, so very important terms, guys. You must know what is mutual induction. Okay, so the coil in which there was a deliberate change in the current and magnetic field is called your primary coil. And the coil in which there was an induced current is called your secondary coil. So you've got two coils. You've got the primary coil and the secondary coil. So the induced potential difference in the secondary coil can be made higher or lower than the potential that is applied in the primary coil, depending on a number of turns. So basically, this is the principle of how a transformer works. Okay, so this theory is very important because it's an extension of application of your electromagnetic induction. So now, before we lose any time, I'd like us to just see some few examples from the Siyavula textbook. Okay, so let me see. Okay, no problem. Okay, so we still have a little bit of time until 11:55, so we can do some of these problems. So now we come to a problem. It says, consider a circular coil of 5 turns. Okay, so already you start by writing your given. So your N, remember we've got EMF is equals to N times change in flux divided by change in time. So now already we've got a circular coil of 5 turns with a radius of 1.73 meters. Okay, so we've got our N and we've got our R. Okay. The coil is subjected to a varying magnetic field that changes uniformly from 2.180 to 12.70 in an interval of 3 minutes. Okay, so the axis of the solenoid makes an angle of 27 degrees to the magnetic field. Find the induced EMF. Okay, so how are we going to work this out? Number one, we know that magnetic field is at an angle to the surface, remember. So a magnetic field is always at a certain angle. And remember, we always spoke about perpendicular to the flow of current. This means that we must account for the angle that the field makes with the normal and the one for the equation, which is in this case our magnetic flux will be equals to the B times A times the cos of theta. Okay, so the starting or initial magnetic field, which is B1, is given as the final, as the field magnetic field, which is BF. So this will be our magnetic field. We want to determine the magnitude of the EMF, so we can ignore the minus sign. So for this case, we're ignoring it because we just want to know what is the magnetic flux. Okay, so the area A will be your pi r squared. So the A, you always need to know that area is equals to pi r squared for a circle. Okay, because remember, we're working with a cylindrical coil. A coil, when you look at it cross-sectional, it's actually round, right? When you look at it on sideways, it will be long, but when you cut it open, you'll see that it's a circle. So that is a circle. That's why we use area as in pi r squared. So how are we gonna okay, so now we come back to this equation and we put our EMF is equals to N times change in magnetic flux divided by change in time. So we know now that we've got two, we've got the before and we've got the initial and we've got the final. Okay, like it's mentioned here, that circular of many turns, the coil is subjected to varying magnetic field that change uniformly from this point to this point. So we know that this one is the final one and this one is the starting one. So that's why we have two in the equation. So we've got the final, the change in magnetic flux is the final minus the initial. So guys, remember, for EMF to be induced, there always has to be a change in flux. You cannot have a constant flux. If it's a constant flux, then EMF will not be induced. Okay, so we can factor out the area and the angle because those are the same, and we can put the magnetic field in two of them. We can have the final, and we also have the initial, and then this is how we can calculate it. So you have your area here. If you want, you can calculate your area on the side and then come and just plug into the equation, just to avoid a couple of errors that can happen when you are, when you are doing your calculations. Because I know it can be very tricky, especially when you're doing an exam. You just want to finish and you're stressed of all the stuff that you don't know. So sometimes it's better to calculate your area on the side, because sometimes you get that a person that's marking your paper is going to mark your area, and if you have written it on the side and it's correct, you might get a mark for it. Okay, so this is what we're going to have at the end. Any questions with regard to this question, guys? This one is very simple because everything was given to you. You've got your magnetic field here, you've got your angle, and you also have your number of turns, and you have your radius. Okay. And then let's move on to number 6, guys. These are questions from your Siyavula textbook, so you can check. It's the exercise questions, so you can also check them as well on your spare time, so that you can be able to reference what you have learned. So it says here, consider a solenoid coil of 11 turns with the radius of 13.8 times 10 to the power minus 2 meters. So what do they say? The solenoid is subjected to a varying magnetic field that changes uniformly. This is what we want, that changes uniformly from this one to 2.7 T in an interval of 12 seconds. Okay, so we have our N, we've got our change in magnetic field, and we've got our radius. And we also have our angle, which is the axis of the solenoid. Here it's stated as 13 degrees to the magnetic field. So here we are given everything that we require for us to calculate the induced EMF. And then they want us to find the induced EMF. And number B, if the angle changes to 67.4, what would the radius need to be for the EMF to remain the same? This one is interesting, guys. So basically here, what it means here is that we would have to make the, if the angle changes, what would the radius, we need to make R the subject of the formula, because everything stays the same and the angle would have changed. So what we need to do, we would make the radius the subject of the formula. Guys, if you're getting confused, please do not keep quiet. Let's work on this so that we can understand it better. I know that we don't have a lot of time, but we've got enough time just to clear out any confusion that anyone can be having. Okay, so the EMF is going to be equals to the number of turns times the change in magnetic field divided by magnetic flux divided by the change in time. Okay, so we have our B's that we is going to be the 13.8. The B's is going to be the 2.7 and the 5.34. Guys, make sure that you stick to your, for example, if here they had written 13.8 millimeters or 13.8, this one it would be centimeters. Make sure, guys, that you do not just copy and paste it the way it is. You're going to have to say 13.8 times 10 to the power minus 2. So make sure you get your SI units very, very correctly. Okay, even here, if they said mini T, then you'd have to say 5.34 times 10 to the power minus 3. So those are things that you always need to make sure that you do correctly. Okay, so there we have it. Now we plug everything that we have into the equation, and then this is what we would have. Okay, why do we have a minus here? Because in our formula we do have a minus there. Okay, it's how the formula is written. Okay, any questions there? Because it's going on the, it's an opposing current. Okay, and then now we move to B. In B, remember I mentioned to you guys that in B, what they want the radius, but they want the EMF to remain the same. So what would be said here, if you get this one wrong, then it's going to be difficult for you to get number B correct because you're using your answer from your induced EMF to plug it onto the next equation. So what would that be? So you see, we just took the 0.14 the way it is, and we plug it into the equation because they said there for it to stay the same. And then you put everything in there, but now we're going to change the angle. Okay, the angle there was 13, and now it's 67.4 because it says if the angle is changed 67.4, what would the radius need to be for the EMF to remain the same? So for it to be equals to minus 0.14. So this is how, it's just a few changes that you're making, but the only problem would be if you got this answer here incorrect, okay? And then this is how you would find your radius. Okay. Any questions there, guys? There's still time to explain if you're getting confused somewhere, or if you have some terminology that you didn't understand correctly. This is your time to ask. Okay, so let's just do one example, one last example before our time ends. Oh, our time is almost up, guys. Okay, our time is almost up. So maybe you guys can go and try this example here at home, okay? And see if you can be able to do it on your own. But let's unpack it here in class before we do that. It says here, consider a solenoid with 5 turns and a radius of 11 times 10 to the power minus 2. The axis of the solenoid makes an angle of 23 degrees to the magnetic field. So what do they want here? Number one, they said find the change in flux if the magnetic field is 12 volt over a period of 12 seconds. And number B, if the angle is changed to 45 degrees, what would the time interval need to change to for the induced EMF to remain the same? So guys, this one is typically very similar to what we calculated on number 6. So here we would have our EMF is equals to number of turns times change in flux, okay, divided by the change in time. But here they want the change in flux, so you don't have to separate them. So here you're just going to make the triangle change in triangle flux as the subject of the formula, okay? So you won't have to have 2 values in this case, because here they want the change in flux as a whole, okay? So there you just make the change in flux the subject of the formula, and from there you can put all these things in your equation and you will have your answer. And how are we going to tackle B? If the angle is changed to 45 degrees, what would the time interval need to change to for the induced EMF to remain the same? So basically here, we'd once again go back to just trying to go to the next slide. Here, we'd go back to the problem that we just did before, which is number 6. If the angle changes, the only thing that what we do here, we make what do the time interval need to change? We're going to make the triangle T the subject of the formula. So you do you write your equation, your EMF equation, and then you make your triangle T the subject of the formula. So that will determine the time interval. So you would have had your radius, the number of turns is there, the radius, which is this one, it doesn't change, and the flux, the change in flux that you get from this answer, you will also have to put in this equation. Put in this equation. You'd also have to put that in the equation, and for induced EMF to remain the same. So now it's going to be changing T, and the induced EMF was already given here as 12 volt. I hope that you guys are understanding this and how it works. So guys, please go and try these 2 problems and see if you can do them, okay? And then because next week we're going to be moving on to the next thing, which is the electric current, okay? So I hope that everything that we've unpacked today has had some meaning. So I don't know if anybody has any questions, any further questions to ask. But guys, I just want to remind you guys again that I know that it's tough, you know, with everything that's happening, with the COVID-19 that's happening. But you know, I think you guys can make it if you just focus on these small little problems. I know that there's other factors that people are dealing with. And guys, please, my email is always available. It's t33t@gmail.com. And you guys can contact me anytime if you're having certain problem, because you know, if you have other problems that you're dealing with, it's going to be hard for you to focus. And for physical sciences, I'm not even including all your other subjects. I know how difficult it can be to concentrate. So if you do have some problems that you need someone to talk to, I'm always available. You can contact me on my email. We can even talk over the phone and, you know, just try and get your mindset into, you know, passing, because guys, you need these marks if you to be good, so that you can be able to apply for your grade 12. So guys, we all made it tough. You know, some of us maybe we had to walk. Back in our times when I was still doing grade 11, it was quite a distance, you know, going to school. But you know, I had to try there, and it was difficult sometimes, having to work overnight. Sometimes there's no electricity. You have to use candles to study because you're writing an exam and you want to get good marks. You can still do it, guys. There's nothing that's standing in your way. All you have to do is just have a strong will that's going to push you forward in order for you to be able to do what you need to do. But I trust each and every one of you, and I know that you guys are going to do well. With physical science, if you understand your concepts and if you understand your theories, sometimes you can even draw diagrams. I mean, you can go to Faraday, because you know, all throughout the syllabus, we use a lot of Faraday's law. You can just draw a mind map and draw all the different Faraday laws in order for you to be able to understand. I know mind mapping helps a lot. So you can put some mind maps and try and write your Faraday laws, try writing your Lenz's law, try understanding how electromagnetism works. And I mean, just understanding the right-hand rule alone, there is going to be marks. There is going to be something that's going to be asked about the right-hand rule. So you need to know those things. So I hope that, you know, everybody is going to try their best and work well. Please try this problem, try these exercises. If you do exercises and you find yourself confused or unable to answer some of them, just send me an email. Not on this one. I forgot to change it once again. I'm sorry. It's t33t@gmail.com. I think I'll try and put it in the chat. If you guys have other problems, I'd like you guys, even if you're using any textbook, you can just text me whenever, anytime, day or night. I'm always available. I'll be there to assist you. You can ask me questions if you're struggling with problems, because I know with physical science, if you don't understand something, you can struggle with one problem for like an entire evening. So do not struggle alone. Let's struggle together. This is a tutoring campaign, and we are here as Africa Teen Geeks to help you guys through your grade 11. And thank you guys so much. My name is Nonkulego Matondo. I am your grade 11 teacher. I am your grade 11 teacher. Let's come back again next week, Saturday, from 11 to 12. We are here doing physical sciences. And please get ready. Do read up a bit of the electric circuits, so that when you come, at least you have more questions to ask. You know, it's always better when you're asking questions of things that you don't understand, rather than, you know, your mind having to reset from scratch on how to do your work. Okay. Thank you guys so much, and goodbye.